Okay, carrying on with chapter 2. The topic of this video is the buoyancy force. So we're going to start talking about the fundamental physics. What's the source of the buoyancy force? Then we'll talk about a sort of a shorthand procedure to calculate the buoyancy force called Archimedes Principle. We'll do a sample problem, and I'll end by talking about the stability of floating objects, which of course is important for things like boats. Okay, we've probably all done this. If you've ever been in the pool and you've played with a ball in the pool, you try and push the ball under the water, and there's an enormous force pushing up. You've probably done that. Let the ball go, and it just rockets out of the water. So the question is, fundamentally, what is causing that upward buoyancy force on the submerged object? It's kind of a mysterious force. Think about this for a minute. Maybe pause the video. Well, a hint is it's related to what we've been talking about. In the previous video, we talked about hydrostatic forces on curved surfaces, and we drew diagrams like this. So imagine this is your ball. There's a little bit of weight, but it's relatively small, as you know, relative to the buoyancy force. And you have a pressure distribution, and the pressure distribution increases with depth. It's always normal to the surface. The arrows up here are very small. The arrows down here are very large. And of course, the net force is in the upward direction. And so you get this upward force that we call the buoyancy force. But fundamentally, it's really the net result of the hydrostatic pressure distribution. So that's the key concept to keep in mind. So in theory, you could calculate and in practice too, sometimes you can calculate the buoyancy force by just integrating that hydrostatic pressure distribution over the surface area of the object. And that would be relatively easy to do for a cylinder or a sphere. But if you had a complicated shape, that could be tricky. So luckily, we don't have to solve this integral, which could be difficult for complex shapes. There's actually kind of a shorthand solution, and that's called Archimedes Principle. Archimedes was a Greek mathematician, inventor, 3rd century BC. And Archimedes' principle states that a body immersed in a fluid experiences, of course, an upward buoyancy force equal to the weight of the fluid that the object displaces. So I've drawn over here an object. Let's say it's a rock sitting at the bottom of a lake. And you have the weight of the rock, and you have the buoyancy force and some normal force here. The weight, of course, acts at the center of gravity of the solid. The buoyancy force acts at the center of the displaced volume. So now for a nice uniform rock or a uniform solid, the center of gravity and the center of buoyancy would be at the same location. But if you consider something like a ship or a boat, which has a hollow hull, the center of gravity and the center of buoyancy, the center of the displaced volumes, could be at vastly different locations. So you've probably experienced this if you've been in a pool and you're standing in the shallow end and your feet are touching the bottom of the pool. You feel that there's a lot less force on your feet. So the normal force required to hold this object in static equilibrium is not just the weight, it's the weight minus the buoyancy force. The weight is obvious. It's the specific weight of the solid times the volume of the solid. That's just the weight of the solid. And then the buoyancy force is the specific weight of the liquid that the body's, we're assuming it's fully immersed, times the volume of the solid. And so I've shown a rock here at the bottom of a lake, let's say immersed in a liquid. That's really obvious that we have an upward buoyancy force. But in everyday objects, the coffee cup sitting on your table, everything in the room is immersed in a fluid. That fluid's air, and you're displacing that fluid. So there is a buoyancy force even on objects that are in gases. But it's generally a fairly small buoyancy force because of the low density of gases. Roughly speaking, that would be about 3 orders of magnitude lower than being in a liquid. So I'll come back to this issue of when the buoyancy force due to gases would be non-negligible. Okay, so let's consider a floating object here. I've got maybe a piece of wood floating in some water. And in that case, for static equilibrium, the weight equals the buoyancy force. So we've got the weight equal to the buoyancy force, and the buoyancy force is just the weight of the fluid that's displaced by the solid. And so it follows from Archimedes' principle that a floating body displaces its own weight of the fluid in which it floats. Of course, again, the weight acts at the centroid, the center of mass of the solid. The buoyancy force, again, it's important to understand this, acts at the centroid of the displaced volume. Let me change my pointer to a pen. So the buoyancy force here acts at the centroid of the displaced volume, which is this hashed area marking with my mouse. So the statics is very simple. It's just weight equals buoyancy. The weight is the specific weight of the solid times the volume of the solid, and the buoyancy force is the specific weight of the liquid times the displaced volume of the liquid. And of course, to float, solid has to have a lower density than that of the liquid. Now, so far, I've just mentioned that Archimedes' principle, this idea that the displaced volume equals the buoyancy force, is kind of a shorthand approach. If you know that, it's very easy to calculate the buoyancy force. So I'm just going to do a quick calculation just to demonstrate the equivalence of the pressure distribution to the buoyancy force calculated using Archimedes' principle. So if we use Archimedes' principle and we look at a cube here, so this is a cube submerged in a liquid of gamma L, and it's got side length L, 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 it's a cube, and it's at some depth H. Archimedes' principle tells us that the buoyancy force here is just the weight of the volume of liquid that cube would occupy. So it's just L cubed times the gamma of liquid. So that's the weight of the displaced fluid. And that's the easy way to calculate the buoyancy force. So now what I'm going to do is I'm going to calculate the buoyancy force using the hydrostatic forces on the top and bottom surfaces. So we have a certain pressure distribution on the bottom surface. We have a certain pressure distribution on the top surface. Of course, we have pressure distributions on the side surfaces, but they act horizontally, so they don't come into the calculation of the buoyancy force. So I'm going to calculate the buoyancy force using this integral of pressure over area, and I've picked a really simple shape. So this is not a rigorous proof, it's just a demonstration that you get the same result. So looking at the pressure forces on this cube here, at this face here, this is a horizontal face, so the pressure at this face acting downward would just be gamma times h. The depth of this face here is everywhere at depth h. So gamma times h times a is the downward force. Further down on the cube at the bottom here, we have a higher pressure because we're deeper in the fluid, and it's just gamma of the fluid, of the liquid, times h plus L, where L is the side length times A. So the buoyancy force is the upward force minus the downward force due to pressure. And if you do the math, noting that the cross-sectional area here that the pressure is acting on is L squared, you can very easily show that you get gamma L cubed, which is exactly the same result we got from just a simple application of Archimedes' principle. So again, the key concept, even though we're going to use Archimedes' principle, because it's an easy way to calculate the buoyancy force, you want to always keep in mind that the buoyancy force is caused by the pressure distribution on the surface of the object. Okay, so next I'm going to do a simple calculation. This is an example from the midterm in 2015. I think this was a multiple choice question. And it says that we have a rectangular block of wood that's floating in some oil. The specific gravity of the wood is 0.65. So it floats on oil with 75% of its volume below the free surface. So I've drawn that here. 75% of H is below the free surface of the oil. And what we're after is to find the specific gravity of the oil that the wood is floating in. Okay, so we just talked about this a couple of slides ago. What's the force balance for a floating object? think about that for a moment before we move on. So for a floating object, the weight equals the buoyancy force. The weight, of course, acts at the centroid, the center of mass of the wood block, which would be the center of volume for a uniform piece of wood. So right there. In contrast, the buoyancy force, now it's not important for this problem, but it will be for subsequent analyses, to recognize that the buoyancy force acts at the center of the displaced volume. That's this blue area here. So you can see it acts slightly below the center of gravity here. And I've just, of course, it would act on the center line, but I've just shifted it off so you can see the location of the buoyancy force. And so we have the buoyancy force equals the weight for a floating object. The buoyancy force using Archimedes' principle, that it's the gamma of oil, which is kind of what we're after. We're after the density of the oil to get the specific gravity, times the volume displaced equals the specific weight of the wood times the volume of the wood. That's just the weight of the wood. And you're told in the problem that the wood block floats with 75% of its volume submerged. So the displaced volume is equal to 0.75 of the total volume. We can make the substitution in here for the displaced volume equaling 0.75 of the total volume, and we get this expression. Now the volume of the wood cancels out on the left and right, and we can divide by the specific gravity, the gamma of water, in order to express this equation in terms of specific gravity. Remember, specific gravity is the gamma of the fluid over the gamma of water, technically at 4 degrees C. So I've divided through by the gamma of water, and here's the specific gravity of oil that we're after, and here's the specific gravity of the wood that we're given in the problem is equal to 0.65. So the specific gravity of the oil is just the specific gravity of the wood divided by 0.75, the fraction that's submerged, and we get the specific gravity of the oil equal to 0.867, which is the answer. Next, I'm going to talk just in a very introductory way about the stability of floating objects. There's quite a section in your textbook about this, but we're not going to go through the mathematics. It's just I want you to be aware of the issue of stability of floating objects. Engineers really need to be aware of this, especially people who are going to be working, for example, in the field of naval architecture. Naval architecture is the engineering stream for the design and manufacture of sea vessels, submarines, offshore structures, that sort of thing. So, of course, floating with the sort of the correct side up would be a critical issue for the safe design of boats, barges. And I added this because it was kind of interesting. It used to be, prior to 2012, there used to be a requirement for the SAE Mini Baja vehicle, which of course is the student competition to build an off-road sort of dune buggy type vehicle run by the Society of Automotive Engineers. It used to be a requirement that the vehicle would float for one of the tests. And of course, students would come and talk to me about how to make this vehicle float such that it floated with the vehicle pointing in the right direction. You don't want it to float with the cab upside down, and that's really a stability issue. It's interesting that this requirement for the SAE Mini Baja was actually removed in 2012 because of safety reasons. So that kind of highlights the problem that I'm talking about. Of course, it's an issue with fishing boats, and there's been numerous accidents. I've shown a picture here that I took from the Globe of, I believe this was a whale watching boat in 2015 that capsized in British Columbia. So just to describe this problem a little bit, imagine an object. This is a wide, not very tall object floating, like maybe a barge floating in water. And we give it a little tip. We tip it a little angle theta here, and that angle is in the counterclockwise direction. If this was a uniform piece of wood, the weight would act at the center of gravity in the dead center here. When we displace at this angle, we have the submerged volume here, which I've colored in red. That's the submerged volume, and the buoyancy force acts at the centroid of that submerged volume. Now, as you can see, the moment produced by the weight and the buoyancy force is in the clockwise direction, in the opposite direction of the initial displacement. So the moment caused by the buoyancy force for a sort of wide, not so tall object restores the boat back to its level position. And there's a general principle here. If we take a center line along this boat that passes through the centroid, and you take the intersection of the buoyancy force with that center line, this is called the metacenter. If the metacenter is above the centroid, then the design will tend to be stable. You give it a small displacement and it'll return back to its level position. So that was a wide, short object. So now let's do that same sort of analysis for a tall, narrow object, which I've shown here. So in a tall, narrow object, you can see that the center of gravity is quite high. It's above the water line of the liquid. So again, we do this, we give it a little displacement, we tip it a little bit in the counterclockwise direction, and we look at the direction of the restoring moment produced by the buoyancy force. Now, the buoyancy force here would act at the center of the displaced volume. That's the displaced volume. I've even shown it would actually be probably a little bit more over here, but obviously the centroid of the displaced volume would be somewhere around here. And you can see now that the moment produced by the buoyancy force and the weight is in the counterclockwise direction. So this boat is going to continue to tip. It's going to tip even worse. It's going to be unstable. It's going to overturn. And so the counterclockwise moment will act to increase the small displacement angle theta, and this design will be unstable. And if you look at, again, the center line here that passes through the centroid, and where the buoyancy force intersects that center line is called the metacenter. In this case, the metacenter is below the center of gravity, and in that case, we get an unstable situation. This kind of design would be unstable. It wouldn't want to float in this position. And that explains why, for example, you can't take a pencil. Try floating a pencil on its end. It'll always want to lie down in the water unless you add some weight to the bottom of the pencil and lower the center of gravity. It also explains why if you're on a small fishing boat and there's an upper deck, there'd be a maximum occupancy on the upper deck. So you don't want everyone running up to the top deck and raising the center of gravity such that your boat becomes unstable and capsizes. I mentioned this problem earlier in this lecture. I talked about how all of the objects in this room are immersed in air, and you are displacing air. So there is a buoyancy force due to the displaced air. My question that I would have is that, does the buoyancy force affect the reading on your bathroom scale, or is this a negligible effect? So another way to think about this is, if you could weigh yourself in a vacuum, the health impacts of being in a vacuum notwithstanding, of course, but if you could weigh yourself without displacing air, would that change the weight on your scale? Think about this for a moment. The answer is, if you could weigh yourself in a vacuum, you would weigh a little bit more. You are displacing air. It's not large. It's not zero either. The volume of a typical human body, depends on the person, of course, it's about 60 liters. So you're displacing about 0.06 of a cubic meter. You multiply that by the density, and you get that the upward buoyancy force, of course, I've got this as 0.07 kilograms, or about 0.16 pounds. So it's small. It's about 0.1% of your weight. So we usually neglect it, but you should recognize that it's not zero. So if you're weighing, steel or something that's very high density relative to the density of air, then you're probably okay to neglect the buoyancy effect. But you should really keep this effect in mind. Imagine if you were trying to weigh, in other words, by that I mean find the mass of a piece of styrofoam. You put this on a weigh scale and you measure its effective weight. That weight needs to be corrected for the fact that there's an upward buoyancy force because it's displacing air, and the density of the air that it's displacing is not that different from the density of the polystyrene. So if you don't make that correction for the buoyancy force, you will find that your estimate of the mass of the polystyrene is incorrect. Okay, the next video is a slightly more complex example. It involves a long wood bar or spar hinged at A. Its volume is half submerged in a liquid of some sort, and you're given the specific gravity of this wood bar, and from that information you have to do an analysis to find out what the specific gravity of the fluid. This is a variation on the example that we just did, but a little bit more complicated, not terribly more complicated. So if you feel comfortable, you might have a go at this problem and then watch the video and see if you got the analysis correct. And that completes this presentation. I included this diagram here just to remind you to always keep in mind that the buoyancy force is not some mysterious magic force. The buoyancy force is a result of the pressure distribution on the object. And that completes this presentation.